Institute in the 90s, yeah, and his supervisor was Yuri Vasilievich Kapaev, yeah, and then he moved to Europe, to Germany, then to Spain, and part of the audience, of course, knows his beautiful work in the field of superconductivity, yeah, and okay, today he will discuss anomalous currents, magnetic response, and magnetic interactions in two-dimensional superconductors, yeah, something like this. I cannot see it behind. Okay, so,
okay, thank you very much. Yeah, it's a bit unusual with this high technology.
Probably you can just
Should I press?
Take a seat.
Понятно? No?
No.
It's not that high. It's not that high. Good. And now it works. Oops. Now it should work. Ah, I should click back. Okay, good. So thank you very much. It's a pleasure to be here in this very unusual surrounding with these screens, wise, high technology. But that's very nice. Okay, today I will present part of my activity which is related to superconductors with spin orbit coupling, and the class of phenomena related to the so-called anomalous currents, which are related to very fashionable these days, the superconducting diodes effect, the finite effects, the anomalous Josephson effects. I will not be talking about this, but I present some qualitative picture of anomalous currents in superconductors and the related manifestations of these currents in magnetic response, in particular in paramagnetic response, and the finite size effects in paramagnetic response of the superconductors. The manifestations in magnetic interactions, namely the interactions between ferromagnetic islands or magnetic impurities embedded in the superconductors. These are my collaborators, my friend and long-term collaborator, Sebastian Bergeret, with whom we wrote most of these works in this field, and the postdoc, young postdoc in the mesoscopic physics group and material physics center in San Sebastian, who was involved in the second part, in the problem I will discuss in the last part of this talk. This is outline. I start by introducing the concept of anomalous currents, the concepts of spin charge conversion, both in normal and in superconducting systems, and their relation to symmetry. Then I switch to specific phenomena, to the finite size effect in paramagnetic response of these superconductors with spin orbit coupling, and eventually discuss the magnetic interactions induced by these supercurrents. This is my main system, the 2D system, which with a broken reflection in the plane of a 2D system, yeah, in this plane. So which means that the top and bottom of this 2D system are different. And this difference introduces the polar vectors, the natural direction perpendicular to the plane. And the presence of this polar vector makes the system gyrotropic. It's first of all, it's a polar symmetry. Yeah, it's a C infinity V form of the symmetry group. This is a polar system, and any polar system is gyrotropic. What is the gyrotropy from the point of view I needed? This is a possibility to make a connection between different geometric objects, vectors and pseudo-vectors. Yeah. In particular, having the polar vector, I can start from a pseudo-vector, sigma, for example. Is it visible? Yeah, the pointer. Yeah, good. Yeah, so I can start with a pseudo-vector, which could be spin, for example, make a cross product with a polar vector, which I am internally available in my system, and this makes a vector. So I converted the pseudo vector to the vector. I can make the scalar product of this object with another polar vector, for example, with momentum, and I get a scalar. The scalar is something which can appear in the energy, and the vector is something which can be electric field, the polar vector, electric field, charge current, or something like that. Yeah, so the presence of a polar vector gives me a possibility to convert pseudo vectors to vectors. And this phenomena appear in the systems with a gyrotropic symmetry. So it's a certain lack of certain symmetry. With a lack of certain symmetry, I cannot distinguish between vectors and pseudo vectors. And because of that, I can make such connections. This simple system, and these are the possible physical realizations. These are, for example, all Rashba systems, semiconductor quantum wells, asymmetric, Rashba surface bands, Dirac surfaces of topological insulators, any 2D systems, any 2D superconductor deposited on a substrate. Because on one side we have vacuum, on the other side we have a substrate, and top and bottom are different, and then I have naturally appearing the polar vector. Conversions.
So, let me ask you. So in principle, even if you just have a field.
Yes, I have a film. I have a film yeah. which is deposited on something yeah. in such a way that one surface of this film has one property and the other surface of this film has another property. I have already natural polar vector. Okay. I have natural polar vector, and I have a possibility to convert vectors to pseudo vectors, and this gives the possibility to
But in general, it's not perpendicular to the surface, yeah.
Okay, I'm for simplicity, I'm considering the situation when it is perpendicular to the surface, but in general, of course not. All I'm talking about will be valid for any system with a gyrotropic symmetry group. And this is essentially all polar groups, the chiral groups, all CN, all OT. Yeah, anything which lacks inversion and lacks certain reflections. Yeah, so there are, as far I remember, out of 22 non-central symmetric point groups, there are 19 or 18 which are gyrotropic. I think 19. Yeah, so there are three exceptions. So it's not necessary. Very frequently in this business of superconductivity, people are talking about the non-central symmetric superconductors. Actually, this is not really true because lack of inversion symmetry is not necessarily implies the gyrotropy. The example is the gallium arsenide. Gallium arsenide, which is TD symmetric group, it's not central inversion, but it is not gyrotropic. It has too many reflections. And because there are too many reflections, there is no way of making a connection between vectors and pseudo-vectors. Yeah, so in that sense, the gyrotropy, this is the precise definition of what we need. And this specific case, which is very easy to do artificially, like just depositing a film, isotropic film depositing on something, it makes this natural polar vector, which is perpendicular. Yeah, so for simplicity, I'm considering that. But most of the conclusions are valid for any gyrotropic system. Okay. I mentioned the conversions between spin and charge, because spin is an axial vector and the charge, for example, the charge current is a polar vector. So this makes a conversion between spin and charge degrees of freedom. And there are different flavors of these conversions. And I start with the simplest one. I'm sorry, but here the titles are not visible, yeah, right?
You also, for
yes.
Us in
but okay. Yes. No, you also don't see it. Yeah, that's it. Okay, what's written here is the spin Hall effect. Yeah, that the spin charge conversion, the first type of a spin charge conversion is a spin Hall effect. spin Hall effect is the connection between the charge current and the spin current. The charge current, J, small j, is a polar vector, and the spin current is a second rank pseudotensor. So converting charge current to spin current or spin current to charge current is a conversion of a second rank pseudotensor to the polar vector. To do that, I need a coefficient which is a third rank pseudotensor. And the third rank pseudotensor exists everywhere. In 3D space, we have simple the Levi-Civita tensor, epsilon ijk. It's always there. And because of that, the spin current can be always converted to the charge current. And because of that, the spin Hall effect, which is the transformation of charge current to spin current and then back, it is an absolutely universal property of nature. It exists everywhere, in sodium, everywhere. Yeah? The point is that we need spin-orbit coupling for that, because we convert spin degree of freedom to the charge degree of freedom. We need spin-orbit coupling, but because in nature, spin-orbit coupling is always present, only the amplitude, the value, the strength of spin-orbit coupling varies from material to material. The spin Hall effect is absolutely universal phenomenon. It exists everywhere. In the isotropic system, in the isotropic inversion symmetric system, like platinum, any standard material, in any standard material, we see the spin Hall effect. In the inversion symmetric cubic with a cubic symmetry, the spin Hall effect is described by the epsilon ijk vector. In 2D system, if flows, the spin and the charge flows are bound to the plane, then the direction of the flow bound to the plane, then the spin polarization in this isotropic 2D system is always out of plane. Yeah? So the spin Hall effect in the 2D system is always conversion between the charge current and the spin current polarized out of the plane. We will need this statement later on. Another type of spin-charge conversion, which is of my primary interest here, is the connection between the spin polarization and the charge current. Spin polarization is an axial vector or the pseudo vector, and the charge current is a polar vector. And for this, we need a gyrotropic. We cannot, without having, for example, in this specific situation, without having a polar vector, I cannot make a polar vector out of the axial vector and vice versa. But if this vector is present, I have a 2D system with different top and bottom, I can make a cross product out of this n vector, the normal to the plane, and the charge current or the electric field. And this is an axial vector, and this can be already proportional to the spin. In principle, this gives me a spin galvanic effect. So out of the charge current, I can make a spin. This is called the spin galvanic effect, or for specific Rashba case, Edelstein effect. In reverse, out of the spin and the vector normal to the plane, I can make a polar vector by making a cross product, and this gives me a polar vector. So it looks like from the spatial symmetry, I can make out of the magnetic field or the spin, I can make a current. But I know that, for example, in the ferromagnets, I do not see uniform current. Yeah, so the space symmetry is not enough. There is another general concept, which is a gauge invariance, which restricts the possible connection between the charge currents of electric fields and the axial currents in the form of a spin. First, let's look on a normal system. What's written here is a spin galvanic effect in normal conductors. Supposed to be that, as far I remember. Let's consider what is called the spin galvanic or Edelstein effect. I apply an electric field to the conductor with a finite conductivity, and I generate a spin polarization out of the charge current or out of the electric field. By applying the electric field, I polarize my system actually polarize like that. To make such a polarization, I need the conversion response function, the second rank pseudotensor, sigma Ka, where A is the direction of the spin polarization and K is the direction of the applied electric field. if my system is 2D and it has the internal polar vector, I can very easily make such a tensor out of the epsilon ikk, out of the third rank pseudo tensor and the n vector. And this gives me the pseudo tensor of Edelstein conductivity. Now I can go deeper to microscopics, and because of the gauge invariance, my electric field can be related to the time derivative of vector potential. It is proportional to the omega times AK. And this Edelstein conductivity can be related to the Kubo correlation function between the charge current and the spin apparatus. And the Edelstein conductivity contains, because of that omega, it contains the I omega as usual in the conductivity. It contains the I omega in the denominator, which implies that if I have a static spin galvanic effect, that is a spin polarization, static spin polarization generated by the electric current or by the electric field. This implies that the correlation function, this Kubo correlation function, is proportional to omega. What does it mean? If I now look on the inverse effect and use the reciprocity relation, then the response of the electric current to the Zeeman field, to the magnetic field, is given by the same correlation function. And since this correlation function vanishes as omega, at small omega, the charge current can be only generated by a time-dependent magnetic field. It is proportional to the B dot. And this is why just plainly by statically polarizing material, we cannot generate the current. We do not generate the current. The gauge invariance forbids this. Because of the gauge invariance, the charge current, the inverse spin galvanic effect, is proportional to the rate of spin generation in the normal system. The situation becomes dramatically different in superconductors. In superconductors, we have the phase gradient, and we can construct the linear gauge invariant form, linear in the vector potential, which is a superfluid velocity. I may add to the vector potential the phase gradient, and this combination is already gauge invariant. And because of that, the gauge invariance cannot forbid the static Kubo correlation function between the spin operator and the charge current operator, which means that in a superconductor, I may generate the supercurrent by the static Zeeman field. And this is very different, and this is conceptually different. First of all, by applying a supercurrent, say constructing the superconducting state with a non-zero phase gradient, I will spin polarize my system, which is the same essentially as the normal spin galvanic effect. The spin polarization is generated by the current, in this case a supercurrent, but the inverse effect is very different. I apply a static Zeeman field, I produce a spin polarization, and because of the spin polarization, I generate a supercurrent. These two relations actually can be translated to the Lifshitz invariant, the form linear in the superfluid velocity entering the energy of a superconductor. Indeed, I can, out of my n vector, the polar vector, and the Zeeman field, I can construct the T-odd polar vector, and I can multiply it with the T-odd polar vector superfluid velocity to get a scalar. Just as a side comment, this T-odd polar vector has a symmetry of toroidal moment. Yeah, so there was a very old activity in the group where I was grown up, and there was a very old work by Sasha Gorbatsevich, which, as far as I remember, called the toroidal moment as a generator phase. So that is basically this. It's very closely related to the superconducting inverse spin galvanic effect. So it's the bottom line of this. In gyrotropic superconductors, so in superconductors with gyrotropic symmetry, of course, in the presence of spin-orbit coupling, which is always there in general, the static Zeeman field generates a supercurrent, and this is called the anomalous current. Yeah, so when I apply the Zeeman field, I generate a supercurrent. Of course, the supercurrent just cannot flow simply. There should be a special geometry topology. Yeah.
So can it be understood in a simple way that you have two pseudo vectors, magnetic field, and this normal vector to the plane, and then you can generate a real vector current by cross product?
Yes, sure. Here it is. Yeah, this. There are different manifestations of the anomalous currents generated by applying the Zeeman field. First of all, that the generation of the phase gradients in a finite system. If I have my finite system, of course, current cannot flow. So it should be stopped by something. Yeah. So if I apply my Zeeman field parallel to the field, it would generate the anomalous current proportional to n cross h, but then the current should vanish. In the big bulk system, current should vanish, and it is vanished by creating the phase gradient. So the phase, automatically my system, the self-consistently generates the phase gradient across the system, and this phase gradient generates a counterflow in a sense, yeah, so which cancels completely this anomalous current. So what I have at the end, I have the superconductor in a helical state. So in a state with the phase linear dependent on the coordinate. And this is precisely, one can say that this is a phase generator. That's why I have this polar vector, and this polar vector generates a phase gradient. This phase, because of that phase gradient, the anomalous current is cancelled, and I have the finite static system. If I would have the torus topology, or if I would close this phase, then in principle current may flow. If I apply the Zeeman field parallel to the cylinder, then there will be current flowing. Nothing forbids. Yes. In this case, I cannot generate the phase gradient, right? Because it should be periodic. So that means that in that situation, I will get the current flowing. In the Josephson geometry, this translates to the so-called finite junction. Yeah, so the Josephson junction, in which in the state of zero current, I have the built-in phase difference. Well, that was the proposal, first proposal made by Boostin long ago, the finite junction. So this is a very general, again, very general situation of the gyrotropic superconductor in the presence of the in-plane magnetic field. If I make a connection between these two electrodes, then the current may flow. Yeah? If I would enforce the same phase, then there will be current flowing. This automatically implies the asymmetry of the current phase relation. So the current of minus phase not equal to the minus current of phase, which automatically, more or less automatically, in general, implies the asymmetry of the critical currents of the Josephson junction, depending on the direction of the flow. And this,
in fact, it's not total, because they can be.
There could be special cases when the current phase relation contains only single harmonic.
Yeah.
When the shift of the current phase relation does not necessarily implies the different phase. But in general, this is a kind of exceptional situation. Yeah. In general, if we have the not trigonometric,
not so exceptional actually, because in many experimental situations, we have single harmonic,
which essentially we in general we have more, right? But the rest are just small, yeah. So which means that this difference between left and right critical currents is simply small. Yeah, so but generically by symmetry it is there. Yeah, it is not not there by symmetry. Yeah, by symmetry it is there. It can be just small. Okay. I'm not going to discuss this phenomena. I'm going to discuss something different. First, the modification of the paramagnetic response of a superconductor. Yeah, what is the paramagnetic response? I apply the Zeeman field and the system response. Yeah, normally the metals just polarize. It's a Pauli response. They polarized in the direction of the field. In superconductors, if I apply a weak Zeeman field, superconductors are singlet, as superconductors are singlet. And we cannot, by weak Zeeman field, destroy those. This is a singlet, or the spectrum is gapped, and until I didn't close the gap, the polarization is zero. It is known that experimentally it is not zero. It is not zero because of spin-orbit coupling. And that was the first, I don't know whether that was the first proposal by Abrikosov and Garkov. Maybe it was at first, but the actual theory was first because of them. And then later on by Garkov and Rashba, the same result was obtained for the intrinsic spin-orbit coupling due to crystal felt. But that's not the end of the story, because if the superconductor is gyrotropic, like the Rashba superconductor, then, as I explained, there are the current flow. There is this anomalous current. And then the question is how these anomalous currents modify the paramagnetic response. And that's what I'm going to discuss next. Oops. So first, I remind what is the paramagnetic response of the superconductor. We apply a Zeeman field to the Hamiltonian of a superconductor. And then technically, and actually this is very good. This is also, there is a deep physical content. The response is naturally split into two parts. The Pauli response is the Pauli susceptibility, and that is what we have in a normal metal. And the spin generated by the triplet condensate. So I have, and these two contributions have different scales. The Pauli response is on the scale of the Fermi wavelengths. It is a very local response. And the polarization of the condensate is on the scale of the coherence length. This can be visualized in the following way. For example, I put the ferromagnetic insulator on top of a superconductor. Then in the immediate vicinity, because of the magnetic proximity effect, I have here the Zeeman field applied to a superconductor. And then immediately here, locally, the superconductor is polarized, like in a metal. And this is this local term. But then the triplet condensate is also created, and it is created non-locally on the scale of the coherence lengths. Totally, because my superconductor remains singlet, this local spin polarization is exactly compensated by this non-local. And the total spin is zero. There is no response. So polarized condensate fully screens the local polarization of a metal. If I would just solve that problem, it's very easy to solve. One can see that this is indeed the case. So my distribution of spin is not locally zero. Yeah, it is non-zero right at the magnetic field if it's inhomogeneous, and then it's compensated on a large scale. And of course, this is not what people saw experimentally. Yeah, experimentally, there is this problem of a night shift. Yeah, so essentially, there was a problem in 50s. Yeah, that experimentally, one measures the paramagnetic response of a superconductor. And this is explained by the presence of spin-orbit coupling. If I have impurities with spin-orbit coupling, or if I have crystal field spin-orbit coupling, then in combination with a certain randomness, it causes the spin precession, and this leads to the spin relaxation. The normal system, this is the cause of a spin relaxation. In the superconducting system, by exactly the same, technically exactly the same, in the kinetic equation, technically in exactly the same way, it causes a relaxation or suppression of the triplet condensate. As a result, this excess spin, which exactly compensates the local contribution, becomes smaller than it was without spin orbit cut. And this compensation becomes not complete. And since there is not complete compensation, there is some remaining paramagnetic response of a superconductor in the presence of spin orbit coupling. So that was the first theory in 60s, 62 by Abrikosov and Garkov, and then Garkov and Rashba did it for the Rashba superconductor, for the 2D Rashba superconductor, which is qualitatively very similar and qualitatively the same, if the system is infinite or in the bulk. Now I'm going to understand what happens if the system is finite. And first, I go a little bit back to the to understand deeper physically the origin of the anomalous current, which is the main physical entity not taken into account in the standard theory of the paramagnetic response. By symmetry, if I have the polar vector perpendicular to the plane and I play a Zeeman field, I can construct the polar vector in plane, and this could be the current. This is the anomalous current. Yeah, now let's try to understand a bit deeper the origin of this current. I know that in a superconductor, when I apply a Zeeman field, I create this excess spin, the triplet condensate. And spin orbit coupling, crystal field spin orbit coupling, it works as a momentum-dependent Zeeman split. In this momentum-dependent Zeeman splitting, the momentum-resolved spin polarization, this excess spin, precesses, and because of that, it naturally generates a spin current. So essentially, the application of the Zeeman field first polarizes the system in the presence of the crystal field spin orbit coupling, and second, it generates a spin current. What sort of spin currents it generates, it's easy to understand again from the symmetry consideration. Out of the spin produced by the spin polarization and the normal vector, I have for the 2D system, in my situation, I may have only two second-rank pseudotensor, either this plane direct product or the pseudoscalar times the unit tensor. Because I'm interested in the situation when the magnetic field is in plane, only this remains. Yeah, because I apply my magnetic field, I spin polarize my system in the x direction, and this produces the spin current flowing in the direction of the Zeeman field and polarized out of the plane. Then I apply the spin Hall effect conversion from the spin current to the charge current and recover the original, my original anomalous current. But now I can understand what will happen if I put borders here. This is the bulk discussion. Yeah. Now what I have the spin current flowing in that direction, which generates a charge current flowing in that direction. And now I can very easily understand what happens if I here and here put boundaries. If I put boundaries, then the spin current cannot flow. It should be zero at the boundary. How it can be zero at the boundary? Only if I generate the diffusion spin current. So I must generate the spin accumulation at the boundaries in such a way that near the boundary, my spin gradient will generate the spin current, diffusion spin current, in such a way to kill the bulk charge current at the boundary. So it should be localized, because what happens in the bulk I know. And then near the boundary.
The boundary is insulated.
Yeah, just infinite flows. So the boundaries from which my spin current cannot penetrate. Just a finite system. I'm talking about the finite size effect, finite superconductor. From here, I understand that in the system restricted in this direction, in the direction perpendicular to the applied Zeeman field, I should generate the spin accumulation polarized out of the plane, which should be localized here in such a way to compensate exactly to zero the bulk spin current. And this will automatically, by the spin-Hall relation, will automatically generate the edge counterflow of a charge current. And because this and this must be zero, then this counterflow should exactly compensate the charge current flowing along the boundary. So my charge current, this anomalous charge current, will be concentrated only at the middle region of the sample, and then it will go to zero at the edges. This is the automatically follows from the zero spin current at the boundary, at the impenetrable boundary. But of course, I know what happens in the bulk. In the bulk, my charge current, if the system is also restricted in this direction, my charge current will be compensated by creating the phase gradient. Yeah, so at the middle, I will generate the phase gradient and kill my charge current. And then at the end, there will be the counterflow. And then there will be something what remains. That the qualitative situation is the following. I apply my Zeeman field. The Zeeman field causes the spin accumulation at the boundaries, which rotates here in the other direction. This generates the interfacial counterflow and the bulk anomalous current. That is, only this red was in the bulk. And now I produce here, because of this counterflow, because of the gradient of the spin density, I produce the interfacial current flowing in the other direction. And then if I eventually forbid the charge current flowing through that boundary, so just to put another boundary condition, zero boundary condition for the current through that wall, what will remain is only the closed contours near the edges. Because here, near the middle of the sample, the anomalous current will be compensated by the phase gradient. But of course, the phase gradient cannot compensate it uniformly everywhere because the current is varying. And then what will remain is only the contours, the closed contours of the current. And in addition to the spin polarization, to the spin angular momentum, at the edge of the sample, I will generate also the orbital angular momentum, the orbital magnetization.
Does it mean that you should get voice there?
It's too weak, actually. Yeah, that's because probably in the situation with people frequently ask that. Yeah. Yeah, that is obvious. Yeah. In all these effects, because of the spin orbit coupling, they're weak. Yeah. So actually, it's a little current here. It's not a vorticity, yeah, so it cannot carry vorticity. Probably vortices can be pinned by that. But automatically you will not generate it.
I'm a little bit I'm confused by your explanation because look, in the middle you say that you have phase gradient, yes? Mm-hmm. And then you have this counter current close to the edge, and then I'll start to calculate the integral of the phase gradient along the certain contour. Yeah, look, should I get zero or not? Because it should be
you'll get
2
zero.
by n.
You'll get zero. You'll
get zero.
Yes. Okay, let's go a little further because better there will be some formulas there. Okay. Yeah, so how you do this? Sorry. Yeah. So the first, that's a good question. Yeah, maybe I'm not right. Yeah. So this is the qualitative picture. Yeah. So then what we did in reality. Yeah, so essentially the qualitative picture appeared after the calculations. Yeah, so it frequently happens. Yeah, so what we did, we used our Uzadl theory for intrinsic superconductors, and we computed first the response to the Zeeman field for the stripe. Yeah, so the system which is opened in that direction. Then by applying the magnetic field, if you apply the magnetic field this way, then exactly in agreement with what I said, what we see, first of all, the spin polarization. This is the red is the X polarization. This is a polarization along the Zeeman field. And then we generate also this spin accumulation out with the out of plane direction, the spin accumulation here. If I now compute the current, simply take and compute the current, then what I see, I have here the bulk anomalous current, which goes to 0 at the edges. Yeah, so there is a counterflow because of this spin contribution, say the whole effect caused by this spin current due to the spin gradient. Yeah, so then that's the distribution of the current which we have. Just for information, which is very easy, if I would apply my Zeeman field out of plane, then what I generate, I do not generate anomalous current. I simply generate the H response like one would usually expect for the response to the orbital magnetic field. But this is due to spin orbit. Yeah, but the symmetry is the same. Yeah, so I have like a current contours due to the out of plane Zeeman field. Yeah, there is no orbital field here. I apply only Zeeman field. This is the Zeeman field generated the counter flows at the edges. Okay, now what I'm doing next, I use this distribution of the anomalous current and I plug it into the continuity equation. Yeah, so I have my continuity equation. Then in my current, I have the anomalous current computed microscopically plus the supercurrent due to the phase gradient and possible vector potential, because this is a charge current. I have to take into account the magnetic field of this. And I solve the continuity equation, which is the essentially Poisson equation. Yeah, so this anomalous current works technically. It works as a source as a built-in vector potential. Yeah, so that's it, like an internal built-in vector potential, non-self-consistent. This is what I get out of the solution of my microscopic system, and then I solve the Poisson equation for the phase. Poisson equation for the phase together with the Maxwell equation for this vector potential, applying the boundary condition that at all ages, the normal component of the current is 0, yeah, in particular at these ages. Yeah, so now we can already discuss what happens if, yeah, if I would be in the bulk, then simply bulk, say, there would be no these boundaries, yeah, somewhere. There would be no these boundaries. Then by saying that my current must be 0 at these ages, will automatically generate me constant phase gradient to kill this A. And then I satisfy everything, boundary conditions and the equations. There will be no vector potential, this one, because there will be no current. Now, since my A is non-uniform, it behaves like this. My phase gradient also will be, there will be some distribution. One can solve this equation. There will be some distribution. But essentially in the practically everywhere, because here the superconducting scale is a microscopic scale. All this is valid when my psi naught, when the coherence length is much smaller than the size of the sample. Then essentially practically everywhere, if I neglect this magnetic field, practically everywhere, I have a Poisson equation. So I have a Laplace equation. So I would say that the contour integral is, I would say it's probably everywhere zero. At least this equation can be solved.
But
in certain limiting cases.
Conditions and the normal derivative of the phase is zero. Yeah.
Normal derivative of the current is zero of everything. No, normal derivative. Okay. The normal component of the current is zero.
Okay.
I do not see here possibility to create a vortex.
Yeah.
Essentially, I have.
Usually, if you want to create vortices, you should add something like rotor of the gradient of phase equals to the set of delta functions.
Yeah.
And then you should compare the energy of the state without these peculiarities.
So the point is that this A is proportional to the spin orbit coupling strands. It's a kind of peak perturbation, I would say. If I would solve this as we solve it, what we have this kind of current patterns, which are proportional to the H current after all. Yeah, so this H current, which is the integral, under this curve. Just a net H current. This acts as a source here. And what happens is that the continuity equation simply requires that this current just should go somewhere. I generate it at the H, but it cannot stop. It should go around. Yeah, it should return. And that's what the continuity equation does. Probably if the strength, if this amplitude would be large enough, of the order of one could probably think that this could work as a pinning center for the.
I just remember some paper by Sasha Putin with others, where they considered a sort of stripe put on superconducting film, and just in the origin of this stripe, they had this kind of the current, as you discussed, because of spin orbit, and outside the stripe, this effect is zero. Yeah. And this is a sort of similar to your term because it's inhomogeneous. Yeah. In PRP, that's several years ago, but well, and they considered possibility of formation of vortex anti-vortex chains. Yeah, and I remember they had a sort of.
Here, I would say it's highly doubtful because of the energy scales. If I have this weak energy, vortex costs energy, right? As an excited state, probably yes. As a ground state, I doubt because we add a little.
Doesn't depend on W value, because if you have a long stripe in this direction, then probably just the distance between vortices is large. Because you have some gain of the phase, just moving in your y direction. Look. I'm not sure. Sorry.
I'm also not sure. Yeah,
but maybe it's reasonable to look into this paper. Yeah, because it's sort of
there will be something very, very close to what you say in the next part of my talk.
Okay, sorry.
Yeah, so that is probably what you meant. Yeah, it's closely related to this.
Yeah, exactly. The paper by Mashukov also, Alexei Samakhvalov talks something like this recently.
So essentially, what I discussed up to now is that situation. Yeah, it's a situation when I have a ferromagnet, and I put on a ferromagnet the superconducting island in such a way that my current cannot go out. I generate my anomalous currents here, I generate the H currents here, and after all, I'm getting the the current like vertex like patterns at the edges. What happens if now I put the magnet on top of a superconductor? Yeah. Then I generate my anomalous current underneath of the magnet in the superconductor. And then it kind of emanates out. And it should close inside the superconductor. Yeah, so that's then I have like a vertex-like dipole. Yeah, so it's like a vertex anti-vertex pair. Yeah, like this. And this is the next situation. Yeah, in principle, that's always generated. Yeah, so that this is current patterns must be generated. They have like this dipole distribution of the current lines. And of course, if I put several of those, I put another one nearby, then these currents will be interacting, and this will produce the interaction between the magnetic moments on these islands. And that's basically what I wanted to discuss next. I still have some time, right?
You have some time, but still let me just ask you. I will just repeat my questions, but in some different form. Look, say you have some stripe, well, or like circle, whatever, yeah? You have some modulation of phase along this region, yeah? But outside, you do not have this modulation. Energetically favorable, I mean, yeah? And this means that there should be vortex shift because you have linearly changing phase along your stripe and no phase outside. And you always have a sort of vortex change.
Why?
Well, just because
we have
the sum of something which doesn't depend on without phase. You always
actually, the solution is more complicated. It's not like this, because this situation with the magnet, with a small magnet in the superconductor, it is analytically solvable in a very simple way. Here is a solution. This is a solution of a dipole, of electric field of a dipole, and I do not see where I can add here the vertices.
It just for your case, when you have this circular region, it's just question of the size of the region.
Okay.
Increasing the size, I think you always should get a vortex. I'm considering
increasing. What would be this?
Look, this is not circular object like you.
Yeah. Okay.
Here you have this gradient of phase.
Yeah.
And here it's zero. Yeah. Okay. And because of that, the psi function will be proportional to some sort of, this is x direction, this is y direction. It's a sort of y. Yeah. And this is some y. And you get phase splits. Always. You should get vortices. It is in fact the result of this paper which I mentioned. One of them. Yeah.
Okay. Good. I will think, but I'm not totally sure, and I'll tell you why. Yeah, because
what you're saying is that this K is small. That's true, of course. But it's just question of the distance between words.
And what would what's the scale you would expect?
1 over K. Distance between vortices will be 2 pi divided by K. Yeah, it's not obvious.
And then you would generate one vertex.
Yeah.
Okay.
Exactly.
That's good. That could be. That's probably could be.
Yeah. For your circular region, like we show here.
Yeah.
Question of the size of the region.
That could be. If you make it as large as the that's
okay. Sorry, maybe we should continue.
Yeah. So that's okay. So now I turn to that situation. Yeah, I put my magnet or the Zeeman field. I put it locally on top of a superconductor. Then then the anomalous current is generated only here underneath, and then this super magnetic island works as a source of a current. And this source of the current generates the current, which should go around. And of course, it is described by the continuity equation. First, I consider a very simple situation. I will forget that the charge current generates a magnetic. Yeah, I simply look on the current where there is the contribution to the current proportional to the superfluid weight, the superfluid density, the phase gradient, and then the anomalous current, which exists only underneath of a small magnetic region, of the magnetic region. This works as an effective built-in vector potential, which is perpendicular to the magnetic moment and to the normal to the vector. Yeah, so this green line is the direction of the anomalous current, and this red line is the direction of the magnetic moment. And then what I should solve the continuity equation to determine the distribution of the phase. Yeah, so the distribution of the phase follows from solving the continuity equation. And this A, or the anomalous current, is something localized in that region. And what I have essentially the electrostatic problem for the electric field or the displacement vector or electrostatic potential generated by the polarized insulating sphere, where this A is an insulating sphere. So my anomalous current works as the polarization of the insulating sphere. The ds grad phi is an electric field, and J as a meaning of the electric displacement. And from this electrostatic analogy, I can immediately write a solution. This is a 2D. Yeah, so I have like the 2D problem, 2D electrostatic problem. I can immediately write the charge current, which is essentially the displacement vector generated by a polarized disk in a 2D space. And this is, of course, a dipole pattern. This is a 2D dipole, where the integrated anomalous current plays the role of the total dipole moment of the insulating disk in a 2D space. Now I can think how the other magnet will interact with this object. Because this is a current, and the other magnet also generates a current. The current is a kinetic energy, and of course, energetically, I would like to reduce the kinetic energy. So, which means that the anomalous current generated by the second magnet should be oriented perpendicular to the current superflow generated by the first magnet. So, which means that the magnet put in this direction would like to be oriented parallel to the first one, or the current in the perpendicular direction, the y direction, would like to be oriented anti-parallel. But in 2D, this and this amplitude of this, like the ferromagnetic and anti-ferromagnetic interaction, which are oriented in the line connected or perpendicular to the line connected to points, they are just numerically the same. So the dipole interaction decaying in this direction and in this direction in the pure 2D electrostatics are identical to each other. What happens that if I would take into account the magnetic field, so which means that in my energy, in addition to the built-in vector potential, the anomalous vector potential generated by the small magnet, I will take into account the fact that the charge current generates a magnetic field, and solve everything together, then what happens is that the corresponding current distribution generated by the magnet will be given not by the solution of the Laplace equation, not by the Green's function of the Coulomb-Green's function, by the log 2D, but by the Keldysh potential, which is very funny. Yeah, so the Keldysh potential, that's those who know something about excitons in 2D materials.
It seems to me that before this work by Keldysh, there was some...
There was a Rytova, yeah, killed.
Yeah,
Yes, yes.
So
okay, it used to be killed the Rytova potential.
Right.
Yeah. Okay, so essentially the funny thing that the dipole pattern generated in this type of superconductor generated by the small magnet can be viewed as a Keldysh dipole distribution. And because of this special feature of the Keldysh potential, the decay in this direction is slower than the decay in that direction. In such a way that if I take into account, so the Keldysh potential is something which looks like the screened Coulomb potential at small distances, which are smaller than the characteristic scale. In the case of electrostatics and the Keldysh-Rytova potential, this is the polarizability of the 2D plane. And in this case, this is the Pearl length of a 2D superconductor. When the distance is much smaller than the Pearl length, this is like a log, it's a Coulomb potential. And when the distance becomes much larger than the Pearl length, it is screened, but it's not screened, but it just becomes power law, is 1 over R.
In superconductors, we know like vortex.
Yeah. So that's and here we have like a couple vertex anti-vertex, which are not quantized. So again, I have this small effect. Whether it is possible here to get vertex anti-vertex, I don't know. Maybe when we will make this island very big. But that's another question. Yeah, what is important here is that the orientation, the ferromagnetic orientation of the magnetic moments becomes preferable compared to the antiferromagnetic orientation. In the case of the absence of the magnetic field or a pure Coulomb vertex, so to say, pure logarithmic vertex, there is a degeneracy of the orientation, that there could be any orientation in such a way that the angles differ by pi. And if I take into account the magnetic field, the Pearl screening, then the two magnets want to be parallel and directed along the line connected them. And this in particular makes the possibility to order ferromagnetically the lattices. That's my last slide. Yeah, that's yeah. So that if I put the magnetic regions in a lattice, then for any Bravais lattices with the Bravais lattice, 2D Bravais lattice, with the only exception of a square lattice, the orientation, so the lattice want to be oriented ferromagnetically. So in a sense, if my system turns to be superconductor, then it becomes the ferromagnetic ordering of the impurities. So that's like the funny manifestation of the anomalous currents, which are generated in a gyrotropic superconductor. So the first of all, that's like the home take messages, yeah, that in the superconductor, the spin galvanic effect, this is essentially, it can be understood as the generation of a current, as a current generators created by the magnetic region, by the Zeeman field. And this is the origin for all these phenomena, which is a helical superconducting order, anomalous Josephson effect, the superconducting diode effect. All these can be traced back to the superconducting spin galvanic effect. The spin-orbit coupling, together with geometry, what it does, it creates the macroscopic current patterns around inhomogeneities on a system. If I have inhomogeneities with boundaries or magnetic regions, then around these inhomogeneities, we generate the macroscopic current patterns, which modify both the paramagnetic response and in particular can lead to these exotic manifestations of the gyrotropy in a superconducting system as a ferromagnetism generated by superconductivity. So that's all. Thank you very much for your attention.
Okay, let's And it's nice story. And now questions. Maybe first, I would like to ask people from Zoom. Do you have any questions? Can you hear me? Fortunately, maybe it's possible to press this button.
This one?
To see, yeah.
No,
Like this one.
So,
This two.
which one? This?
No.
This.
This one.
Okay.
Okay.
No one is here.
No, they are here.
They're here.
Why? Okay. No questions. Yeah, then please.
Yeah, my question about experimental side. So, are there any experimental efforts to see this?
Okay, there were attempts to measure these patterns, these patterns, and I think the results are still inconclusive. Yeah, there are speculations for superconductors, like as far I remember, this is iron diselenide, where people it's still not published paper from Chinese group, where they seemingly observe ferromagnetism of magnetic impurities generated by superconductivity. Yeah, that's related to that. And explicit visualization of these patterns we discussed with experimentalists, and they attempted to do this, but unfortunately the problem is that we were thinking that maybe one could measure this the magnetization, the H magnetization generated by these patterns. For example, by some like STM probes with magnetic sensitive probes. But the problem is that the currents are weak. So formally, if we formally compute the magnetic moment, then it scales like a width of that. Yeah, so it becomes it can become as large as you want, but actually it is very distributed.
Okay.
Yeah, so the magnetic field which you would try to sense is sufficiently weak.
More questions?
Yeah, I have a question. So regarding your last part where you mentioned that you kind of induce the paramagnetic interaction between some ferromagnetic islands. Let's take a look at an even simpler picture. You have just, let's say, two magnetic impurities in your superconductor, and on one hand you have this chiral interaction that creates a ferromagnetic interaction, and on the other hand you have an RQQI, just usual RQQI interaction. So how these two compare to?
They scale very differently, because these the RQQI interaction it decays on the scale of the Fermi wavelengths, yeah. And this is really macroscopic. So that's much larger than Xi0. So for me, even this many nanometers, the coherence length is a very small scale. So that's really macroscopic.
I guess there is some maybe basic problem with the observation of the effects of interaction of these magnetic particles because of this effect, because of the following thing. Look, you have these magnetic dots, yeah, and you get this dipole-like distribution of currents around, but of course to observe them you want to get them stronger. Yeah? But as soon as you get them stronger, there appear bodies and antibodies, which in fact screen, they kill this effect because they create countercurrents. And the stronger is your effect, the more is the concentration of forces.
In a sense, probably yes. Yeah. So the point is that the hope is that this is a large scale effect. Yeah. So there is nothing on that scale. And from that point of view,
maybe because it's a long range.
It's a long range. It's not necessary to make it as strong to generate to generate vertices. But essentially, generation vertices. That's an interesting question.
It's in fact revealed by Alexey Smatov, who considered this effect. He just studied the energy of states with different number force centers. Okay.
I think in that setting, when the magnetic region is really magnetic impurity, so which is of the scale which is much larger than the coherence length, I do not really see how you can insert vertices there.
For this kind of force, probably yes, yeah.
If you make
it depends on the size.
If you make it large, then probably yes.
Yeah, this is true. More questions.
I have another question. So regarding creation of the current by Zeeman field. So my question was that if I were to incorporate Coulomb interaction into the structure, so would Coulomb interaction suppress this effect or not? Because usually when we have a gradient in phase and Coulomb interaction, the Coulomb interaction actually suppresses, creates a gap to any kind of situations.
Coulomb interaction in which sense? I do not see how the Coulomb interaction may change anything here. If I have my superconductor, then what did
maybe you can discuss it later after the seminar. Okay, more questions? Okay, so let's thank our speaker again. Yeah, and this is small gift. Good.
Very good.
Yeah, it's
thank you.
Abrikos.
Usually.
Okay. So, thank you all. Ну, очень интересно. Спасибо. Самый такой задать вопрос. А вы доклад. Там мы проводим конференцию на английском, и там в рамках аналитики, и в том числе аналитики, но там есть почти. И туда приезжает, в общем, довольно много людей, спорящих, и как это